In this segment, we'll do some more examples of the LZW compression, and we'll summarize the algorithm. So the example from the prior segment illustrated the general LZW compression algorithm, and we'll look at decompression in a later segment, by the way. Summarizing the algorithm. 1. Start with a dictionary having one code per original symbol. Use as many bits per symbol as needed to represent the entire alphabet. In our example, that was 2 bits. And convert the input symbols into equivalent output codes. On each step, pick the code that represents as many of the next input symbols as possible. Initially, that will be only one symbol per code, but as we add codes to the dictionary, we may be able to represent 2 or more symbols with a single code. After each code, call it C, is output, then add a new code that is C plus the next input symbol that C did not include. The new code presumes that C plus next input symbol is a pattern you'll see later in the input. When you do, the new code will be able to represent that pattern compactly. And then 4, when the number of codes passes a power of 2 boundary, so that one more bit is needed to represent all the codes, extend every code by a bit. At any point in the compression, all codes are the same length and can be distinguished from one another in the continuous sequence of compressed bits. Now, of these, point 3 is the hardest to remember. It's easy to figure out what code to use, to output it, and then say, okay, we're done with that step. But a given step in LZW is not done until you add a new code to the dictionary. It's never pick the longest possible code and output it. It's always pick the longest code and output it, and then immediately add a new code that extends the one you just used. Question 1. If LZW is given English text to compress, predict some of the codes that may find their way into the dictionary after a sufficiently long compression. And alternatively, what if the text were some other language instead? Coming back from a pause, in the case of English text, there'll be codes for common letter sequences and even short words, ing, the, an, and, etc. And for another language, the dictionary would have common sequences and words for that language instead. This is a good example of why LZW is effective. It automatically builds a dictionary that reflects common patterns in the input it's compressing. Question 2. Say we'd started our example with a different input sequence, but the same initial 3-entry dictionary. After we'd output 15 codes, how many bits per code would we be using? So it's not this input sequence, some other, but still 3 symbols. And if you think you need to know the actual input to answer this, think more carefully about point 3 in the algorithm summary above. So after you've output 15 codes, you'll have how many bits per symbol? Per code, I'm sorry. Coming back from a pause. At this point, we'd have 18 codes in the dictionary, since we add a new code for every code we output, regardless of what the codes represent. And thus we'd need 5 bits per code at that point. So another LZW example here. We've got a second LZW in our notes, and it's there for you to try from scratch. And we'll do it in stages via an in-lecture question series. As for the first example, we have an alphabet of 3 symbols and an initial dictionary with 3 codes. So, question 3. What are the first 3 codes that will be output? And how many bits will each occupy? And what does the dictionary look like after the first 3 output codes? So, coming back from a pause there, the first code we'll output will be 10 for C, but then, because C was followed by B, we'll add a code 311 representing CB. Now, the next code we'll output will be for B, 01, and both of those are 2-bit codes, but now we're going to add a code 100, code 4, representing BA, and we'll add a bit to every code so that from now on our codes are 3-bit values. And then third code will be a single code to represent A, 3 bits, 0, 0, 0, and we'll add a code 5 representing AB. So, 3 codes have been output, 10, 01, 000. 3 codes have been added to represent CB, BA, and AB respectively. Now, question 4. Continue on for the next 3 codes. And the same questions. What's the output? How many bits per code? And what gets added to the dictionary? Coming back from a pause, our next 3 operations, we have a BA in the input, not yet compressed, and we have a code for that, code 4. So we'll use that and add, of course, code 6, representing BAC. So next up is CB, and we have a code for that, which is code 3. So we'll output code 3, but then it would have been nice to have had CBB, so we'll add code 7, CBB for that. Next uncompressed symbols are BA and, in fact, C. We can get all 3 of them in a single code. Our code 6. So we output code 6, add code 8, which will represent BACB. And we're now in 4-bit code world, so we're going to add 0 to the beginning of each of our codes here. And that's where we stand. So, next output, 100, 011, 110, 3 new codes added to the dictionary, and we're in 4 bits. So, question 5. Finish up the rest of the compression, the whole bit, so to speak. And coming back from the pause, there's really just one more output code now, and that's 1000, representing BACB. Now, this last step is an interesting one. It happened in the earlier example also. We created a code on one step and then used the newly created code on the very next step. And that pattern will be important when we look at decompressing these sequences, so please remember it. It is possible that you might create a new code, as we did when we compressed BAC and wished we'd had BACB, and then immediately use it on the very next step. So question 6. What sort of improvement do we get this time over the simple alternative of using 2 bits per symbol throughout without adding to the dictionary? And coming back from a pause, we output 20 bits. So the 28 bits we would have had to output, 14 symbols, we improved on rather significantly. It's interesting to consider cases where LZW works especially well. So question 7. What would the output look like if I started with our 3-symbol dictionary, as we did, and compressed a sequence of, say, 15 A's? So the initial sequence looks like that. How many bits long would it be, and what content would the dictionary have by the time we were done? So coming back from a pause there, we'd start with the same dictionary as we said. Our first output would be code 0 for an A, but then we'd add code 3 representing AA. So 2 zeros there. Our next output would be 11 for 2 A's, using a code as soon as we created it there, right? And we'd add code 4, 3 A's, and extend everything to 3-bit mode here. So the first 2 codes are 2 bits, and after that 3 bits. Of course, The next code we'd output would be the 100 that we just added. And we'd add code 5, 101 for 4As. And of course, we'd be outputting that for our 4As right away. And add code 6 for 5As, which again we'd immediately use. And that would be it. A total of 15 A's represented in 5 codes, comprising a total of 13 bits. Now, this is the extreme example of LZW at work, as each new code extends the prior one and then is immediately used. Question number 8 here, one more just for fun. Assuming we start with the standard initial 3-symbol dictionary, the following bit output is not possible. Why is it not possible? And at what bit can we be sure that it's not possible? So, coming back from a pause there, if we break it into codes, that would be 01, 10, 100, and right here, 111. That's not possible. We don't have a code 6 by this point. We only have a code 5. And we can tell something is amiss at the second bit right here. So that's where we know for sure something's wrong. Now, a bit of external research for you, and a question 9. What did the letters LZW stand for? What major software compression standard was subject to patent litigation regarding its use of LZW? And when did the patent expire? So, coming back from a possibly long pause, LZW stands for LectureB, the algorithm's creators. Welch's improvement in particular made LZW widely successful and was the subject of a notorious early software patent that prevented free use of the GIF compression standard, which is built on LZW. The patent expired, thankfully, in 2003.